What's up, AP Calculus students? It's Mr. Ford here with another homework tutorial. This is 4.3.1. I'm trying to get a little ahead of the game by making these a couple days in advance. So, I'm recording this on Friday the 21st, and we'll see how far I can keep this up. Anyway, we're going to be doing all of the problems in this set because they're all important, and that's a theme you're going to see going forward a little bit. So let's just jump into it. This is intended as a homework tutorial, not necessarily an understanding guide, just maybe help check your answers and guide you through the problems. 4.109 is going to ask us to evaluate the following integrals, and we're going to do that by any means possible if we can. For the definite integrals, like this one and this one, we're going to actually evaluate them. And for the indefinite integrals, like this one and this one, we're just going to put a plus c at the end and be done. So, regardless, we're going to need to think antiderivatives when evaluating an integral. So, question A, the antiderivative here, the capital F of x. There's not going to be enough room here, but I'll set it up at least. The capital F of x is going to be the sine of x, since sine of x is derivative of sine is cosine. So we're finding the antiderivative. What we require here, actually, what am I even doing at this problem? I haven't looked at it yet. That's a pi, that's a pi. This is 0. Anytime when the integral goes from a number to itself, it's just going to be 0. So moving on to the next question. For question B, we're going to have to take the antiderivative here. This is an indefinite integral because of the lack of any sort of numbers on the top and the bottom of this thing. So we're just going to take the general antiderivative and put a plus c after it. That's going to be pretty tough to do. It might be better or helpful to first of all write this as 5 times y to the 1/2 power. This is our original f of x minus the sine of y. Actually, it's a f of y, not an f of x, since the main variable is y. And you see that in dy also. Anyway, for the antiderivative, the capital F of x, we're going to have to do a little bit of head math here. We're going to increase the 1/2 by 1 degree to make it 3/2. And then we really have to think about, okay, 3/2 times what number is going to give us 5? So kind of the thought bubble up here. 3/2 times what x is going to equal 5? The best way to solve this would be to multiply by the reciprocal. So whatever 5 times 2/3 is, 10/3 is the number we're looking for there. That will cancel it out. The 3/2 multiplied by 10/3 will become 30/6, which is 5. Beautiful. We should also do minus plus the cosine of y, since the derivative of a cosine will be the negative sign we require. And then, of course, we're going to put a plus c on this thing, and that's the end of that problem. Over here in question C, we actually have a legitimate antiderivative to find, whose derivative is 1 over x. This is an interesting one. Now, Now, I'm curious here. Hang on, I'm recording this in advance, and I haven't looked at the thing yet. I don't know if we have the ability to do this derivative yet. I'm just checking to see if we're going to learn. Nope. I'm just checking to see if 4.3.1 is going to actually cover the answer to this question or not. I do not believe we currently have the ability to take the antiderivative of 1 over x. I'm thinking that it is x to the negative first power. That is the original f of x. And so the antiderivative of that, if I follow the reverse power rule, the problem here is going to be it's x to the 0 power. But the problem is that there is a number of different numbers we could put right out there, because 0 times any of them will actually be 0, and that's not going to be the antiderivative. So right now, I think the key thing is in the instructions it says find the antiderivative if you can. And right now, we do not have the ability to do this one yet, based on the skills that we've seen. And now, that having been said, I am going to go ahead and inform you that this is the capital F of x here is the natural log of x. It is true that the derivative of natural log is 1 over x, but we will talk about that at a later date. The same thing is true right away of e also. These ones we can't do right now. We can't do these ones yet. We do not have the skills necessary to do those. You will, by the end of this course, obviously have the skills to do those, but right now, it's not quite there yet. However, over here on D, we totally have the ability. Sine squared plus cosine squared. Actually, these also, I don't think we know how to do these either. Oh, actually, this one's totally easy. This one does require that you know probably the only trigonometric identity that I think you should know and should memorize. The sine squared plus cosine squared, this is the antiderivative of 1 dx. Because the sine squared plus cosine squared is equal to 1. So this is going to just be x plus c. That is the antiderivative that we require there, capital F of x. We will shortly learn how to do antiderivatives of more complex functions. This one up here, question D, is just a memorization one. We just haven't learned that fact yet. And question E is going to require some more advanced integration methods, but for right now, we'll leave those ones alone. Let's look at 110, though. Let's get a little more conceptual. These three graphs below each tell a story. Examine each graph carefully and then complete each part below. Pay close attention to the labeling of the x and the y axis. For question A, we're looking at the graph of y equals s of t. It's a bicycle. Use a complete sentence to describe the physical meaning of s prime of 6. That would be the slope of this curve at s equals, or x equals 6, or t equals 6. Like that would be that slope. That's what the derivative tells you is the slope of that tangent line. What that would be the velocity. Since this is a position function, this is the velocity of the bike at t equals 6 hours. And you might even put the word instantaneous in here, because when we talk about derivatives, the difference is that we're talking about the velocity at an exact point, not the velocity over time, which we usually do. We think about velocity as a slope. Here we're actually thinking about it as a tangent line slope, so at a single instant what the velocity is. Question B, you have the graph of y equals r of t, which involves an employee of a calculator company. Use complete sentences to describe the physical meaning of integral from 0 to 5 of r of t. Now what's important here is that this is a rate. It's a rate in sales per hour. When we take the integral of a rate, we end up dropping the numerator of that, the denominator of that, and we end up with just the top. In this case, the sales of what's going on here. So the integral from 0 to 5 would be physically the area under the curve from 0 to 5. It would be this area right there. But what that will actually represent is going to be the total sales over the first 5 hours. Because when we integrate, we are accumulating things. When we accumulate pieces of a rate, we add them all together and get the total. Question C, the graph of W of t involves a babysitter. Again, I see a wage, hourly wage dollars per hour. So when we take the derivative, or do the integral, rather, we're going to find the actual area under the curve or the number of dollars that they've made. Here, we're looking for the amount of money from 4 to 10 of W of I, di. I doesn't really matter so much, it's just the variable that we're choosing here. This is the amount of money, the total money made from, I suppose this is the time of day, so from 4 o'clock p.m. to 10 o'clock p.m. Just like that. I love these kind of questions for real understanding the connection between derivatives and integrals. We're starting to go beyond the world of just slope and area under the curve and starting to talk about how these things can be useful in different situations. Let's go to 4.111. We have the graph at right showing the velocity in miles per hour of a car during a road trip. At time t equals 0, the car was on the Golden Gate Bridge heading north. Let's write a function for v of t. It's going to be a piecewise function, I'll tell you that much, because we have two separate ideas going on. V of t equals, we're going to open up a little bracket. We just got to do a quick couple of slope-intercept form equations here. It looks like the slope of this line, and be careful on the units here, is 3 hours and 20 miles per hour. So I would say that is the slope of negative 20 over 3. So I would say negative 20 over 3 x plus 20 would be what's going on when, I guess for values for 0 less than or equal to x less than or equal to 4, because that's the function, or I guess it's 4.5. Looks like that's where it's kind of hitting right there. 4.5, like that. Looks like the function follows that line pretty solidly for the first chunk. From there, it's going to be a little more complicated. We have to write an equation for that line, and that's not going to be a very fun thing to do, but we can do it. The calculator can be really helpful here too. It looks like the slope is going to be something like 30, a change in 30, and then 1.5. And if I go on the calculator really quick and divide 30 by 1.5, looks like the slope is 20. So I'm going to put 20x plus. Now, as far as when this thing will hit the y-axis, that's also kind of complicated. I'm just going to use the 0.620, which I see there on the graph. I'm going to use that to, along with the slope of 20, to figure out what the y-intercept should be. Actually, it won't be too tough to do. if you think about y equals mx plus b for a moment, that means that 20 is equal to 20 times 6 plus b. If I just plug the information here, so 20 equals 120 plus b, and that's going to be negative 100 for the y-intercept. So plus negative 100 for values of x that are between 4.5 and 6. This is kind of complicated, but that will take care of at least of our setup there. That's going to help us solve this problem as we go throughout it. Question B, how far north has the car traveled at t equals 3 hours and at t equals 4 hours? Now, this is actually asking the distance, and we're looking at a velocity graph. So what we're going to do is we're going to find the area under the curve. This is pretty simple. For 3, basically this question is asking us the integral from 0 to 3 of v of d dt, and also for the integral from 0 to 4 of v of t dt. Now, the 0 to 3 is actually simple to do. It's just a simple triangle here. We got 20 down here. We got 3 over here. So this would be 20 times 3 is 60. And then we're going to divide that by 2. So that would be 30 miles. Now, for the next little chunk here, we're going to have to think about what's going on there, right there. That, according to a function that we wrote earlier, that right there is the point 4, comma, I got to do some quick calculator stuff, negative 20 over 3 times 4, well, that's not fun, plus 20. It's going to be negative 6.6 repeating, which is not a great thing to know, but that will help us find that little area down there. If you're paying attention, what's happening now is the car is actually traveling backwards since the velocity goes negative. So we'll start subtracting total miles from our journey here. That right there is going to be the area of 1 times negative, yeah, I guess it is negative. Well, we'll make it negative on purpose. It's going to be 6.6 repeating divided by 2. So if we take that and divide it in half, it's going to be 3.3 repeating in that little chunk there. So the car is going to travel back in time 3.3 repeating miles. It's going to be negative right there. If we add those together, this will combine together to make 30 minus 3.333, and it's going to be 26.6 repeating miles. That's that. The question did ask how far north, and so it should make sense that since the graph goes negative, we're going to be subtracting total distance. Question C, what happens to the car from 3 to 5? It's going backwards. It's traveling south, you might think about in this case, because the v of t starts to go less than 0, which causes the car to travel backwards. Set up an integral to represent the displacement from 0 to 6. Very simple to do. Integrals are built for this purpose, 0 to 6 of v of t dt. Very simple. That's just the displacement. That doesn't tell you how far they are, where they are. It tells you how far they've traveled. You would need to know a starting point to figure out where they actually are. That's what question E is going to ask us to do. Set up an integral representing the total distance from 0 to 6. That would be the same thing, I suppose. What is the difference? During the time t equals 0, the car was on the Golden Gate Bridge heading north. So, total distance. I see what we're going to do. For total distance, we're just going to take our answer from the previous problem and just throw it inside of an absolute value. That will take care of any negative parts. Effectively what that does, it takes this little chunk down here that's in the negative territory and flips it up here and then adds it to the rest of the total. Now all the distance is positive. Since total distance, you got to think, when you see total distance, you got to think absolute value of v of t. What you're thinking there. Okay, or, the more I think about it, should that absolute value, you know what? That absolute value should go around the v of t. I withdraw my answer from earlier. There we go. That's what we're looking for. Okay, next question. I think they actually might be the same thing, but okay. 4.1.12. During this course, you've studied the connection between distance and velocity. What's the relationship among position, velocity, and the fundamental theorem? Okay, here you go. There's 3 things you got to know. Position, prime, of t is equal to the velocity. And the integral from 0 to x of v of t dt equals s of t. I guess I said there's 2 things you got to know. If you take the derivative of position, you get velocity. If you take the integral of velocity, you get position. I guess I should say s of t, s of x there would be more appropriate, like that. just because the x would go inside of there. These two things are connected by the fundamental theorem of calculus, which says that derivatives and integrals are opposites of each other, essentially. Question B, considering your answer for part A, write a function to represent the car's position, s of t, from problem 411. So here's how I would think about s of t in question B. What you have to know is you have to know the initial position. We usually call that s sub 0 of t, the initial position, something like that. We don't know it in question 411. They just tell us it's on the Golden Gate Bridge. But if we did know it, let's say we said the car had already traveled 200 miles or something, then we could take that and add to it its change from 0 to x of v of t dt. Actually, let me change some of the variables around here so it's a little more clear. The position at time x would be the initial position, s sub 0, which I'm just going to call s sub 0, plus this integral, the integral from 0 to x of v of t dt. That's what you want to do, because this will tell you how far that car has traveled over time, and x is the main variable. For 113, without graphing, analytically determine where the function f of x is increasing. Increasing means for us that f prime of x is greater than 0. So that's the question we're going to solve. When is this derivative greater than 0? Let's work over here in this space. F prime of x is going to equal to 3x squared minus 14x plus 15. We are not allowed to use a graphing calculator on this one, so hopefully this thing can factor relatively nicely. This is where I always run into problems. We're looking for when this thing equals 0, or I guess when it's positive. So since I can't divide out, usually you'll divide out a 3 or something, but I can't do that here. You know, there are a lot of strategies out there in the world for doing what I'm about to do, but I'm just going to mentally think about it for a minute until I figure out what it's got to be. I need the numbers here and here to multiply out to 15, and I need them to combine together with the x and the 3 to make negative 14 in there. And they have to be positive. So it's not going to be 1 and 15. It's got to be 3 and 5. It's going to be 5 minus 9. That's it. It's going to be minus 5 minus 3, like that. There you go. Yep, that'll work. I love it. Again, I don't have a process for what I just did. All I do is stare at it for a minute and guess and check until I get it to work, and that's what I do. Jordan Disbrow had this thing called slip and slide last year. I do not know what that is. Now you have to set these equal to 0 and solve for the points when this is going to be actually equal to 0, 5/3 and 3. And since this is a parabola, and we know the parabola equals 0 at these 2 points, we know that when it's not one of those 2 points, it's either going to be positive or it's going to be negative. So let's consider that. Usually a number line is kind of helpful here. 5/3 over here and 3 over here. And I like to test the point that's, well, you can test any point you like. Because of the way parabolas work, and because this is a parabola that's going to be opening up because of positive 3 in front, if we know any one of these 3 chunks here, then we can figure out the rest of them. So I like to test 0 because it's really easy. If you plug in 0, you get 15. That's a positive number. That means it's negative down here, and it's positive over here because of the way the parabola will look when it's all done. You could test, say, the point 2 there and maybe the point 4 there just to see if that's correct or not. It is. At this point, we can tell that because it's positive when it's going from negative infinity up until 5/3, and then again from 3 to positive infinity. So this is going to happen. F prime of x is greater than 0 when negative infinity go up to 5/3, and then together again with 3 to infinity, just like that. Very cool. For 114, differentiate the following functions. Determine if it's differentiable. Oh man, I hate when this happens. Now I got to think about where I am. Got to find my work again. This happens when I'm too busy with the zooming in and the zooming out in this program. There we go. Okay, cool. All right, first one's relatively easy since y prime in this case, or dy dx, however you want to write it. The derivative of sine is just cosine. And right now, we're getting toward a point where we have another bit of a formula to do with problems like this, but right now that's fine. Cosine of x minus 3. Over here in the piecewise function, you might be thinking, how do I derive a piecewise function? It's actually really easy. You just take the derivative of both chunks. That's it. So f prime of x is going to equal negative 2x for when x is less than 1. And it's going to be 3 times x minus 1, and that would be it, for when x is greater than or equal to 1. Like that. As far as whether b is differentiable, I should say a is differentiable. We have to determine if it's differentiable for all values of x. This one is always differentiable. It's a cosine function. Cosine functions are smooth, curves, they're boring, they're always easy to do. Question B, though, we kind of have to do the same game with continuity that we usually do here, only now we're talking about differentiability, but it's exactly the same concept. We're going to take 2x, or negative 2x. We're going to take 3 times x minus 1. We're going to plug in 1. We're going to say, does 2x equal 3 times x minus 1 when x is equal to 1? That's the question. Is negative 2 the same thing as 3 times 0? And it's not. So this is not differentiable at x equals 1, because you don't get the same thing there. If it was differentiable, you'd get the same thing representing the same slope, actually, on both sides, but you don't. I don't even know if it's continuous, so I didn't check that. For 115, we're going to write a Riemann sum to approximate 0 to 2 of 6 to the x power dx using n rectangles. This is a concept we did on that circuit training I left for you, and I had my gallbladder taken out. It's actually not too tough to build if you're getting used to this. It's always going to start the same way. It's going to be the limit as n approaches infinity of I equals 1 to n. It's always going to start there. First, let's consider the width of each one of these rectangles. Each one of these rectangles is going to be b minus a over n. So in our case, it's just going to be 2 minus 0 over n. That's going to be the width of each rectangle. And then the height of each rectangle is going to be f of a plus b over n, or sorry, delta xi. So we got to think about what that would look like. That will be, in this purple parentheses, it'll be 6 raised to the 0. A is going to be 0 because it's right there. And our delta x is the 2 over n. So it's going to be 2 over n I power. That would be it. That's all I got to do. That's all I have to say about this. We're going to keep seeing problems like this every once in a while. I know they're still tricky, but just keep working on them. Just keep playing with it. You'll get it eventually. You'll get the hang of the length times width piece going on there. And finally, for 116, a function has a derivative of f prime equals that function. If f of 0 equals 0, what was the original function? So here, this is kind of a preview question for a skill coming down the line, where we're going to find what's called the exact antiderivative for a certain point. Right now, you can tell me that the antiderivative of that function is going to be, let's see, it's got to be x to the third, so 2x to the third. That will give you your 6x squared when you take the derivative, plus 6x squared, because that will give you 12x when you take the derivative, minus 7x plus c. This is the general antiderivative for any function. And as we've seen, there are an infinite number of these functions that have that derivative up above because of the plus c. However, if I suddenly say, hey, f of 0 equals 0, now we can actually solve for c. Because what this means is that if you plug in x to be 0, y has to be 0. Translation, 0 equals 2 times 0 to the third plus 6 times 0 squared minus 7 times 0 plus c. And if you work that all the way out, 0 equals c. This means that the original function, f of x, would have to be 2x to the third plus 6x squared minus 7x plus 0. That's the exact function that has this point and also this derivative. For part B, we're going to do the exact same adventure, only this time, what if x was negative 2 and y was 25? What c would make that happen? So this time, we're going to do the same kind of exercise. 25 is going to equal 2 times negative 2 to the third power, plus 6 times negative 2 squared, minus 7 times negative 2, plus c. Again, they've given us x and given us y, and now we have to solve for c. Find the exact derivative. It's going to be the exact same function as problem A, but it's going to have a plus or minus some number at the end of it. And that's the goal, is to find that number. We're going to work this out algebraically. This is going to be negative 16. 2 squared is 4. 4 plus 6 is 24. 4 times 6 is 24. Negative 7 times negative 2 is plus 14 plus c. So if we think about this here, 24 plus 14 is 38. 38 minus 16, I guess I have a calculator, don't I? 38 minus 16 is 22. And so that means that c has got to be 3. So it's going to be the same answer as the previous problem. F of x this time, it's still 2x to the third plus 6x squared minus 7x plus 3. This is the exact function that has this point and also this derivative. I mean, a and b both have the same derivative, but a goes through 0, 0, and b goes through negative 225. Question C, describe how you found the constant of integration. But basically, here's the process. You plug in x and f of x. We used to call it x and y, but here in calculus we say x and f of x. And then solve for C. It's a pretty straightforward process. We'll have a lot of chance to practice that going forward. So, okay, cool. This was a fun homework tutorial. I hope you had a good time. Hope you're watching along with me. And I will see you in class on Monday. You guys are awesome. Keep it up.